All right. Next lesson is on momentum and collisions. All right. So this is going to be new information here. So a couple things, and I want to make sure we don't get confused. When we are talking about momentum, we denote it with a lowercase p. All right. So not to be confused with uppercase P, which is going to be power. Now our formula is going to be lowercase p equals mass times velocity. So pretty straightforward. All right. Our units for momentum are not easy. All right. Again, our unit for mass is kg, all right, times velocity, which is meters per second. All right. Now, another way we could say this would be newtons per second. Because again, kilograms times meters is going to be newtons, right, over seconds, right, so, or times seconds. Anyways, just not an easy unit here. So who knows? If you guys contribute a lot to the physics field, maybe they can create a new unit for momentum named after you. All right. A couple things. Momentum itself is a vector quantity. It's going to have magnitude and direction. Does matter. All right. So simple formula, and we can try applying it here in our first problem with a baseball pitcher hurling a ball at 32 meters per second. The batter's going to crush it, and the ball leaves the bat at 48 meters per second. What's the ball's change in momentum? All right. So feel free to pause the video, and then we will take a look at the solution. All right. This looks more like a turkey leg. All right. So we have our baseball coming towards our bat with 32 meters per second velocity. And then it leaves the bat with a velocity of 48 meters per second. Now notice I'm denoting direction using positives and negatives. All right, so here we have our formula. Momentum equals mass times velocity. And we know that there's a change in momentum, right? And the change is not with the mass. The mass is constant. We see the change with velocity. All right. So we want to be able to define this. So we know our mass is 0.1. And then our change in velocity, right? We're going to start with our final. So 48 minus negative 32. And we end up with our change in momentum is 8 kilograms per meter per second. All right. So typically, again, you can change this, but for the purpose of this class, typically, unless stated otherwise, right, when things are moving left, we're going to say that they are negative, and when they're moving right, we'll indicate that they are positive. Okay. Now, notice that there was a change in momentum, right? This ball was traveling pretty fast, right, 32 meters per second towards the bat, but then when it was hit, right, we have new velocity that's greater and in the opposite direction, right? So there was a force that kind of caused this change, right? Now, we call that an impulse, right? An impulse is a change in momentum. All right. Now we know that momentum is going to be a product of mass times velocity. And since we're not dealing with changing masses, we can define the object's change in momentum as, all right, change in momentum is going to be our mass times the change in velocity which is going to be our net force times time. Right, we can show how that was derived. All right, so we have power times mass times change in velocity. We know that our change in velocity, I'm out of power in my pencil. All right, so we know that our change in velocity is going to be equal to acceleration, right? Because we know that acceleration is change in velocity over time, which also means that our change in velocity is equal to acceleration times time, which I'll kind of indicate here in a sec. There we go. All right. So remember that acceleration is just our change in velocity divided by time, right? And then we can solve for this, right? Which also means that change in velocity is acceleration times time. Okay. So we can plug this into our formula. Change in momentum is going to be mass times acceleration times time. Now look here, right? We have mass times acceleration. Think about what do we get when we have mass and acceleration, right? We get Newton's second law, or net force, and we still have time. Okay. So let's try to see how forces relate to our changes in momentum or impulses with a few of these examples. So we'll do one first, and then I'd like you to pause and do the remaining three. So for this first one, we assume jumps off a desk. When they land, they bend their knees on impact. All right, so first off, you want to think about why, right? Why do you bend your knees? Why don't you keep your legs straight? Again, one reason why is you don't want to break your knees, right? We want to make sure that you're not breaking your legs. So you want to extend that time of impact. All right. So extending that time of impact by bending your knees. So let's take a look at how this is. So we know that change in momentum is mass times velocity, which is net force times time. All right. So think about what's going on here. Out of these four, right, we're just going to focus on these. Think about what's changing. All right. In this case, see that our net force decreases because we're increasing the time of impact. Now, your mass and your velocity stay the same as you were jumping off the desk. Okay. Pause to try these other three. What I would do is just take the same formula here and then indicate what's increasing, what's decreasing. In those specific examples. Okay. Okay. All right, when you're back, look for a second one. We're talking about follow through in sports. Again, in this case, right, when you're following through, your mass is always constant. But as you follow through, you actually increase your velocity, and you increase the amount of time that there is an impact. Talk about cars and car collisions. Right. Once again, the reason why we have crumple zone in cars is we try to extend the time of an impact, right? Which means that the total amount of force is kind of distributed or decreases. You can't change the mass of the car, can't change the velocity of the impact, but you can change the impulse, right? That force. Last one, we have a beanbag, high bounce ball of equal masses, drop from the same height, right? So talking about which one has a greater average force on the floor. In this case, velocity increases and net force also increases. Okay. Now I'll talk about momentum, right? We see momentum and impulse a lot in more violent contact sports. So we think about in football, right, when you have a player that's running the ball, right, they're going to keep running until something stops them, right? They stop their forward momentum. So we can look at an example problem here, thinking about what is the impulse, right, or the change in momentum experienced by these different players. All right, so see for part A, we have the change in momentum, right? It's going to be mass times the change in velocity. So if we're talking about the fullback, right? We have a mass of 115 kilograms. All right, their final velocity is 0. Their initial velocity is 4. All right, so we're going to get a change in momentum or impulse of negative 460, I'm going to say newtons per second. All right, next problem, B. How about the tackler? What's their change in momentum? Now, here's the thing. We know that according to Newton's third law, right, every action has an equal and opposite reaction, right? So our change in momentum is actually going to be the same, but it's going to be opposite. So we see that the player was running east. So in this case, as they come into contact, instead of being negative 460 newton seconds, it's going to be 460 newton seconds. Still moving east. Okay, what's the average net force on the tackler? So you see our change of momentum. It's going to be net force times time. That's another way we could derive that formula. We'll isolate net force because that's what it's asking for. So we get our change of momentum divided by time. Know that our change of momentum was 460 newton seconds. And our time, 7.5 seconds. All right, our net force is going to be 613 newtons. All right, we can see because seconds cancel out. Okay. We have a 1250 kilogram car traveling east 25 meters per second, turns north. Continues 15 meters per second was the impulse of the car exerted while turning the corner. All right, so a couple things we can do. We can visualize this. So we know our initial is going to be 25 meters per second. Now our final is going to be 15 meters per second. Change of velocity, Vf minus Vi. Once again, can formulate this out. Now for this, I can actually use a little bit of trig to solve for this. All right. See that my change in velocity, just use Pythagoras. All right. This will allow me to kind of find our angle as well. Use the inverse tangent function to find my angle. Okay, end up with 50 degrees or 59 degrees west of north. Doesn't necessarily even ask for that, but just want to show that we can find that in a problem like this. Now, really, all we're trying to find is just what is the impulse, right? So using that mass, using that change in velocity, which again, kind of use a little bit of trig to solve for that. All right, and our impulse is 36,000 newtons per second. Now, one thing you'll kind of notice is that momentum, just like energy, is always conserved, right? We have a concept called the law of conservation of momentum. And just very similar to energy in the way we've talked about it, is that our initial energy, our initial momentum is going to be equal to our final momentum. All right, we can expand this formula out. All right. Our initial momentum let's say if there's two different objects and there's going to be a collision, right, with the momentum of each. So when we're talking about collisions, right, the total momentum before a collision is going to be equal to the total momentum after a collision. So another way we could say this is that our final momentum minus our initial momentum is going to be 0, or change in momentum in a collision is going to be equal to 0. Now, we have two types of collisions when we're talking about collisions. We have collisions that are considered to be perfectly elastic and perfectly inelastic. Okay. So, in a collision, elastic collisions, our kinetic energy is conserved. So, prior to a collision between two objects, right? Obviously, if there's a collision, there's going to be kinetic energy. They're moving. So that total initial kinetic energy is going to be equal to our total kinetic energy after the collision. If we have an inelastic collision, that means that kinetic energy is not going to be conserved. All right. So our initial kinetic energy is not equal to our final kinetic energy. Now keep in mind, in any of those cases, momentum is always conserved. And total energy is always conserved. Right. So that's talking about perfect situations, right? And the reality is no collisions are going to be perfectly elastic or perfectly inelastic, right? Somewhere going to be in between, right? And the only times we'll see this are at the atomic or subatomic level, right? Now you think about why, right? Where are we losing some of that momentum to? Where are we losing some of that energy to, right? Think about in a collision, what sort of things Where does some of that energy get transferred? All right. We lose some energy to heat, sound, and then other forms of vibrations. Okay, so let's look at a few different examples of inelastic and elastic collisions on this next page. All right, so inelastic. We have two rugby players, equal mass, collide head-on while traveling at the same speed. So you think about what's going to be their final speed. Opposite directions, going towards each other, same exact speed, they collide. What happens? All right, their final speed, 0 meters per second, right? It's perfectly inelastic. The total kinetic energy initially is not conserved, right? However, is momentum conserved? Yes. Is there energy conserved? Yes. The main thing that's not conserved is a specific form of energy, which is kinetic. All right. Now, let's kind of show this mathematically. Right? So let's say we got two trains. Right? And there's going to be a collision. All right, so initially, say train 1 has a velocity of 12 meters per second. Train 2, velocity of 0. Let's look at this mathematically. All right, so we have momentum for our first train initially. If we're talking about total momentum, right, we would add it to the momentum of the second train. Now, the total momentum between those first two before collision should be the same as the total momentum after the collision. So I'm going to do mass total times final velocity. All right. In this case, the momentum of the second train before a collision is 0. Right, because it's not moving, so velocity is 0. So all the momentum in the system before the collision is due to train number 1, which is going to be equal to the total momentum of the system after they collide. All right. Now, it's asking what is the velocity of train cars after collision. So I'm looking for this final velocity. We solve for that. End up with mass 1 times V1. So the initial. Okay, divided by total mass. Right, so if our momentum of our first train is going to be its mass times its velocity. Plug that all in. And the two train car system after the collision are moving with a velocity of 6.4 meters per second to the right. Okay, elastic collision. Talking about a proton, right? All right, because again, all these physics concepts generally work on the atomic scale as well. Right, so we got two protons, one stationary, one's moving with a velocity of 2 to 10 to the third meters per second. Right, protons are all positive. Okay. So, what's the final speed of the other proton? In this case, because it's elastic, right, we know that kinetic energy is going to be conserved. So the final speed of the other proton is going to be also 2 times 10 to the third. Because in an elastic collision, our initial kinetic energy is going to be the same as our final kinetic energy. All right, let's look at this mathematically. All right, we know that alpha particles are approximately 4 times larger than a proton. All right, and this proton is traveling to the right, 3,200 meters per second, and strikes the stationary alpha particle, doing this in our big particle accelerators. Anyways, it's going to rebound away with a velocity of 1,920 meters per second. So we're looking at what's the final speed of the alpha particle after there's a collision. Okay, so draw it out. We have our proton moving to the right, velocity of 3,200 meters per second. It's going to hit our alpha particle. Okay. And we see that our proton rebounds off with a velocity of negative 1,920 meters per second. And our alpha particle is moving the opposite direction. And we're trying to figure out, what is that? All right. So we can look at our momentum of our proton initially plus the momentum of our alpha particle initially, which is just 0. It's going to equal our momentum of each final and then in this case what we're trying to look for is we're trying to look for the velocity of the alpha particle after the collision. So we can solve for that. So just rearranging my equation to do so. Right. See that couple things here. So I know that the mass of the alpha particle is 4 times my initial mass. So comes things here. This allows me to kind of cancel out these masses, which leaves me with what I have left over. Okay, so final velocity of my alpha particle is 1,280 meters per second. All right. Now again, one thing you can look at, right, when we're talking about law of conservation of energy is see that initially we have a total velocity of 3,200 meters per second, right, and then finally you kind of add those together. Also ending up the final velocity of 3,200. Okay, last one here for this particular lesson. Explosions. Okay, we got a pumpkin. All right. I'll draw this up. All right, inside the pumpkin, is a little firecracker. And there's going to be an explosion. Now we know that our momentum, all right, initially is going to equal our final momentum. So, a couple things. One, I know let's see how well this works. That's pretty well. I know that I end up with two ends of my pumpkin exploding and moving in opposite directions. Right. Now, I'm not going to know the mass of either end, but I am given the velocity of both sides. Now, I see, because I know that my momentum initially is going to be equal to my final momentum, I know that initially, before the explosion, my momentum is 0. All right? Which may seem a little confusing at first. But let's put this together. So I know my other end of the formula, we have mass of our left side times the velocity. All right, this is all final. Plus mass of second side, final. Again, if I want to solve for my first mass, and isolate that, that's going to be negative mass 2, velocity 2 final, divided by velocity F equals negative 2.2, 26, all divided by negative 34, which gives me a mass for my left side of the pumpkin to be 1.7 kilograms. Okay. Now, knowing this, I can figure out my total mass. All right. Mass 1 plus mass 2. I'm already given that one side of the pumpkin was 2.2 kilograms, the other was 1.7. All right, so my total mass, 3.9 kilograms. Now, keep in mind, this is not going to be perfect because obviously I'm sure we would have lost some chunks within that explosion, but generally, right, perfect world, from a physics perspective, that's how we would calculate that out. All right, just one more lesson after this, but that was plenty on momentum and collisions.